Welcome to Lecture 5, the Natural Logarithm and Exponential Functions. So we'll begin with an alternative approach to defining a logarithm. So you may have seen the definition of a logarithm as being the inverse function of an exponential, but with that definition, it's not so clear how to do things like take derivatives or take integrals. So the natural logarithm is defined as the following integral. Natural log of x is the integral from 1 up to x. Now this is our variable of 1 over t dt for x greater than 0. So let's draw a picture of what this looks like. So if this is the xy axis, this is x, this is y, and then the 1 over x, or actually I should probably say 1 over t, but well, this is fine. So this is a function of y equals 1 over x right here. And let's say this is 1 and let's say that this is x. Then the area from 1 to x, that's going to be this area right here. This area is defined to be the natural log of x. And notice that is always greater than 0 for x greater than 1. So that's going to be a positive area. Okay, so what about x less than 1? So notice for when x is between 0 and 1, the natural log of x is defined to be the integral, well, just using our same definition, our integral of 1 over t dt, and that's equal to negative the integral from x to 1 over t dt. So now, suppose x is, if x is over here, well, and then let's draw it like this. Then the natural log of x is the area under the curve here, but it's negative area because we're integrating from 1 to x over here. So we swap the limits of integration, we put a negative sign, and notice that this integral is going to be less than 0. And notice natural log is at 0. Natural log of 0 is undefined. And let's see, is there anything else we want to say? Oh, what about natural log of 1? Clearly, natural log of 1, using this definition, is the integral from 1 to 1 of 1 over t dt. And that's equal to 0, of course. And finally, the derivative, one really nice effect of using this definition is that the derivative of the natural log of x, as we'll see, is going to follow right from the fundamental theorem of calculus. So the derivative is the derivative, or ddx, of 1 up to x of dt over t. And by the fundamental theorem of calculus, the derivative and the integral, these are inverse functions. So this is just equal to 1 over x for x greater than 0. Okay, so let me just make a comment or two. Neither of these are too complicated, but they're both worth mentioning. First of all, because natural log of x is differentiable, that is, its derivative, we said it's right here, 1 over x for x greater than 0, then it is continuous for x greater than 0 as well. Also, it's the derivative of natural log of x is this function here, which is strictly 0. It's going to be 0 for all x greater than 0. that tells us that the natural log function is strictly increasing for x greater than 0, and therefore it's 1-to-1 on its domain, and so it has a well-defined inverse. Now you probably know what the natural log function looks like. It's going to look something like this, but this actually verifies that the function is strictly increasing, and again therefore it has a well-defined inverse. And of course you should know what that inverse is. It's e to the x, as we'll see soon. So the number e you may have seen arise in several different places. It has multiple different ways that it can be defined. Here's one way to define it in this context. Define the number e to be the value of x such that the natural log of e equals 1. So what does this look like? So here's our function, y equals 1 over x, and now e is going to be that number, so that the area under the curve right here is the area equals the natural log of e by definition, and this is the integral from 1 up to e of 1 over t dt equals 1. So this is one of many ways to define the constant e, and it's arguably the most natural one once we've gone down this path of defining the natural log as an integral like this. Okay, so this is a short lesson. Let's finish by reminding ourselves of some basic properties of logarithms and exponential functions. You've likely seen these before, so again, this is a review. If you look in the textbook, you'll see a lot more identities than this, and every little detail is going to be proven using just this integral definition. If you're interested, I encourage you to look at that or to look at some of the details of a few of them. We don't need to go over every single one of these identities, but I just want to show you remind you of some of the most basic ones. So I put the left side of the equation here, so you can pause the video and see if you can remember it on your own before I write it down. So the first one is the derivative of e to the x is, of course, e to the x. This is e to the x is the one special function that is its own derivative, outside of 0, of course. The integral of e to the x, therefore, is also e to the x, now plus our constant of integration. The integral of 1 over x dx is the natural log of x plus c. And now that follows just from our definition in the beginning of this section. And also the natural log of x to the r equals r times natural log of x. And I encourage you to see if you can derive these properties, especially this last one, just from our basic definition of the natural log of x. And let me actually add 2 more on here that you've probably seen way back in high school. These things, so the natural log of x times y equals the natural log of x plus the natural log of y. This is the additive property, or the additive multiplicative property of natural logs. And then there's a similar one, which is the natural log of x divided by y equals the natural log of x minus the natural log of y. So let me call this property 5, and let me call this property, oh no, that's not right. Let me call this property 6. Okay, and then of course there's a lot of other properties you can derive from these, and I encourage you to check for yourself and verify that these indeed make sense. Okay, thank you.